What if we were asked to find the Taylor series of f of x equaling sine of x centered at a equals pi over 2 and its interval of convergence? So how would we do this? Well, let's see. We've got f of x is equal to sine of x. And let's see if we can find a pattern. F prime of x would just be cosine of x. And then f double prime of x would be negative sine of x. And then f triple prime of x would be negative cosine of x. Then f fourth prime of x, well, that will just be sine of x again. And therefore, we should have a pattern. So when we evaluate at pi over 2, x equals pi over 2, we're going to get sine of pi over 2 is 1, 0, negative 1, 0, 1. All right. So what is the Taylor series? Remember that this is going to be f of a, f of a plus f prime of a over 1 factorial, and then x minus a plus f double prime of a over 2 factorial, x minus a squared plus da 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 da, continuing on the pattern. So we get a 1 plus 1 factorial 0 x minus pi over 2 plus negative 1 over 2 factorial x minus pi over 2 squared plus da 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 da. So what's happening here? Well, we only get the squared values, so probably we're going to have some sort of expression, if we get a Taylor series, of x minus pi over 2 to the 2n, right? Because at n equals 0 it works, n equals 1 it would be squared, n equals 2, etc., etc., etc. So we want to sum from n equals 0 to infinity. So we have this term all figured out. Well, and then we have this alternating. Every n, it's going to alternate. So we're going to have a negative 1 to the n. Let's see if this makes sense. 0, all right, it's going to be 1. This first term, this first squared term, it's going to be negative. And then if you follow the pattern, because we're going to have 1, negative 1, 1, negative 1, 1, it should all work out. Then what's happening here? Okay, we have a 2. At n equals 1, we have 2 factorial. So we should have a 2n factorial. And if you want to extend this to make sure that this series makes sense, then you should. It's a good exercise to check that. So this should be the series for the Taylor series expansion of sine when a is equal to pi over 2. This is very similar to the Taylor series expansion for cosine, except for there's a pi over 2 here. Cosine centered at 0. And that's because, remember, sine and cosine are a pi over 2 shift from each other. So now we need to find the interval of convergence. We're going to do that using what? The ratio test. So we can ignore the negative 1 to the n because of absolute values. Go n to infinity of absolute value of 2 to the n plus 1 factorial all over x minus pi over 2 to the 2n plus 1. Then divided by just the n value or multiplied by the reciprocal. So we get a 2n factorial over x minus pi over 2 all to the 2n. Well, we have some cancellation here, and we get this is equal to the limit as n goes to infinity of, well, here we have an x minus pi over 2 squared remains because 2n plus 2, 2n's cancel. Now here we got 1 times 2 times 3 times 4 all the way to 2n factorial. We have this all the way to 2n factorial, but we also have a 2n plus 1 and a 2n plus 2. So when we cancel things out here, we're going to actually have a 2n plus 1 factor down here and a 2n plus 2 factor as well out here. Now what happens when we take this limit as n goes to infinity? Well, in fact, we will get 0 because we'll have, no matter what x is, we'll always have 0. Even if it is like pi over 2 or something like that, as high as it gets, this will always be 0. This is always less than 1. So what does that mean? That means the interval of convergence, it converges everywhere. So the interval of convergence is negative infinity to infinity. So we have our Taylor series and we have our interval of convergence. We don't need to test endpoints because you don't test endpoints for negative infinity and positive infinity. All right, those are always soft brackets. Let's move on.